Assalamualaikum and greetings to all of you. I will continue chapter 4 part 2. So at the end of the class, students should be able to apply the gradient operator to find directional derivative, normal vector to a surface, divergent or curl. So the outlines are scalar, and vector fields, directional, derivatives, and gradient, normal vector to a surface, divergent and curl. Okay, so refer to our notes. First one is scalar and vector fields. Scalar and vector fields. In general, scalar field is simply a scalar quantity that is a function of space and time. Okay, scalar field. Temperature. Example of this temperature, which the T is function of space and temperature, and the unit will be Kelvin. Pressure. P, let's say small p, is function of space and time. Unit is Newton per meter square. Okay, force over area. Your density, say delta, function of space and time. The unit will be kg per meter cube. Okay. Then physical example of a scalar fields. Temperature near a heated wall let's say I have a box and then I put a heat here. So temperature near the heated wall will be, let's say I use this. Will be born darker so this darker region then so this darker region representing the higher value of temperature. Okay. So next, vector field. A vector field in 3D is simply vector quantity that is function of space and time. X, say f, x, y, z, t, at each point of R. Example, a vector is one single vector. A vector field is distribution of vectors in a space and time. A vector is one single vector. Vector field is a distribution of vectors in space and time. Okay. So scalar and vector fields. So first we'll learn about gradient of scalar fields. So sometimes we call them rate of change. So the gradient of a scalar field is a vector field which points in the direction of greatest rate of increase of the scalar field and whose magnitude is the greatest rate of change. Okay. So f, let's say f is a scalar. The gradient of f is the vector. F is a scalar. Then the gradient of f is a vector. The gradient of a scalar function is equal to the gradient of a scalar function. F is equals to grade f is equals to, write like this, that is d over dx, I think del over del x, y plus del over del y j plus del over del z k times with f. So also you can write as del f over del xi del f over del yj plus del f over del z k. So the symbol is called delta, del, or we can say nabla. Okay. So this nabla will be equals to I del over del j k, or I can write as del x comma del over del y comma del over del z plus. Okay, we should go for example 1. So if fx yz equals to 5xyz square minus 2yz square, find the grade f. Find the grade f at 1, 2, negative 3. So as usual, your grade f will be del f or del x. I, no need to write I if you put in this form. Del f or del y, comma, f or del z plus. Okay. So if you differentiate this function at function of respect to x, you will get 5yz squared. Okay. Again, you differentiate this function respect to y, you will get 5x z squared, we have function of y here also, minus 2z squared. Okay, and then the last one, if you differentiate respect to z, you will get 10 x y z minus 4 y z. Done. Okay, so at point 1, 2, negative 3, your del f will be equals to 5, 2, negative 3 squared. And then you have 5, 1, negative 3 squared minus 2, negative 3 squared. Your x is 1, your y is 2, your z is negative 3. And then your z component will be 10 times 1 times 2 times negative 3 minus 4 times 2 times negative 3. So you will end up with 90, 27, negative 36. Done. So example 2 will be the same, but they ask okay, next, directional derivative. Directional derivative. So fx, okay, is derivative in the x direction, which is in I component. Fy is the derivative in y direction in j component. Now we want to find the derivative at any given direction. So the theorem says if the directional derivative as denote the directional derivative of phi in the direction of unit vector u. Okay, denotes the derivative of phi in the direction of unit vector u. So this is unit vector u, and this is f, we can represent as phi, no problem, it's just a notation. So then we can write as duf, this is big F, u is small, as gradient f times with unit vector. Okay, duf denotes the directional derivatives of f in the direction of the unit vector u. Okay, I just put phi is a dummy variable. Okay, so we see some example 3 example. So example 3, in your note, find the directional derivative of fxy 3 minus 2x squared plus y cubed at p12 in the direction of the unit vector. In the direction of a unit vector, we always put cap. Okay, this equals to 1 over 2i. This is given. G unit vector which is given. Okay, this is given. So your solution will be, you have to find the gradient f. So d u is small, d is bigger, and then you have f equals to gradient f time dot with u. So actually this is a dot. Okay. Okay. Okay, del f is a scalar field, u is the unit vector. So first determine the fx, okay, which is in I component at 1, 2, and then fy in 1, 2. Okay. Okay. So then you have to apply the dot product. Okay, so fx xy. So if you differentiate this f respect to x, you will get negative 4x. And at 1, 2, you will get negative 4. X equals to 1. So fy xy equals to, we differentiate this f respect to y. The first one will be 0, first term 0, 0, and it will be 3 y squared. At 1, 2, you will get 12. Okay. So since the unit vector given as u1 over 2i minus square root 3 over 2j, so you can say u1 equals to half, u2 equals to negative 3 over 2. Okay. 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 So the directional derivative f at 1, 2 same as fx 1, 2 u1 because this is a dot product, and fy 1, 2 u2. Okay, so the formula itself is del f dot u cap. So this f consists of fx and fy, no fz, fz is 0. So here u1 and u2, so you have to dot. Okay. Okay, so this will be negative 4 u1 will be half plus fy will be 12 times negative 3 over 2, negative 3 over 2. So this is negative 2 minus 6 at 3, or approximately negative 12.3923. So you need, in this case, you need unit vector, given direction, need P point, and then you need gradient f. Okay. So this is for direction derivative. And then we see some example, next example. For find the direction derivative of f, the directional derivative of f x, y, z x sine yz in the direction of v, they give vector, not a unit vector, 1, 2, -1 at the point P130. Okay, so only is vector given, so you need to find unit vector. So to find this unit vector, remember the magnitude itself, the vector itself over its magnitude. Okay, and then you have to find the gradient of f at 130. Then you have to find the directional derivative at 130. That is gradient f 130 dot the unit vector. Okay, we will do. So remember from the formula, f, should I have to put like this? So for simplicity, I just leave it as del nabla f dot u cap. So this is a dot product. So you need fx, fy, fz. For the u unit, u1, u2, u3. So this means fx dot u1 plus fy dot u2 fy okay fy dot u2 plus fz dot u3. So we have an idea. So now we do fx xyz will be sine yz. So at 130 we'll have sine 0 0. Fy xyz is x cos yz times with z. Okay, at 130 also 0. Okay, then fz xyz same as from the f. Okay, x sine yz. Okay, then you will get x cos yz times with y. So at 130 as the point given, you will get 3. So we have 0i, 0j, 3k, right? So your del f at 130, usually we write smaller, is 3k or simply 0, 0, 3. You can write also as 3k. Enough. So we have v. They given as 1, 2, -1. So to find u cap, unit vector will be v over magnitude of v. Okay. So this is 1, 2, -1, and then over magnitude square root 1 squared plus 2 squared plus -1 squared. You will have it 1 over set 6, comma 2 over set 6, comma -1 over set 6. Okay. So directional derivative is fx130 u1 plus fy130 u2 plus fz130 u3. So of course you have 0 0, right? 0 plus 0 plus 3 times negative 1 over z6. Okay, so you will end up negative 3 over z6. Okay, you have to dot with u, so u is u1, u2, u3. Okay, okay, from example 3 just now, this is example 4. From this example 3, in what direction from the point P equals to 1, 2 is the directional derivative fxy a max or a mean, and what is the magnitude of this maximum or minimum? Okay, so from this example 3, we have f equals to 3 minus 2x squared plus y cubed at 1, 2, and then the gradient f is fxi plus fyj. So your fx itself is negative 4x, negative 4xi plus 3, fy will be 3y squared, 3y squared j. Okay, so at 1, 2, this will be negative 4i plus 3 times 2 squared, which is 12j. So the direction of the maximum directional derivative del f will be negative 4i plus 12j. So this is the maximum directional derivative. Okay, but if I put negative f, negative del f, or negative nabla f, this will be 4i minus 12j. And this will be the minimum directional derivative. Okay. And then the second question, what is the magnitude of this maximum and minimum? It is nothing, but it's just find the magnitude of the maximum and minimum. As I said here, positive del nabla f will be the maximum, negative nabla f will be the minimum. Okay, so from here, the magnitude of the maximum direction derivative will be square root, we can write like this, square root negative 4 squared plus 12 squared, which is equals to 4 square root 10. Okay, and then the magnitude of the minimum direction derivative will be negative, remember this, the minimum of the direction derivative will be negative 4 square root n. So this negative shows decrease, and then this positive shows increase. Okay. Okay. Okay, next. Example 6. Let t x, y, z is 80 over 1 plus x squared plus 2y squared plus 3z squared be the temperature in degrees Celsius at point P x, y, z in a metal solid. Find the greatest decrease in temperature at point 1, 1, and 2. So remember the word greatest, which means the magnitude, and then this decrease mean negative magnitude of F. Okay, so these some keywords. So solve this. I think you can do it. So first you have to find the gradient T. The gradient T, it is del over del xi plus del t over del y j and del t over del z k plus. Okay, so if you differentiate del t del x, you will get negative 160 over x over 1 plus x squared plus 2y squared plus 3z squared squared. Use the quotient rule. Del t del y will have negative 320y over plus x squared plus 2y squared plus 3z squared squared, and del t del z equals to negative 480 z over 1 plus x squared plus 2y squared plus 3z squared squared. So at P 1 1 negative 2 at point T, at point P 1 1 negative 2, so del T you can factorize square over 1 plus 1 squared plus 2 1 squared plus 3 negative 2 squared squared. Okay, again this is in I. Okay, I can put in I form. 4 plus 2 1 j, I just factorize, and then plus 3z k, which means 3 negative 2. I have to substitute 3 negative 2k. So then you will get negative 5 over 8i. After you simplify, you get negative 504g 10/4k. Okay, remember we have the word greatest decrease, which means the magnitude of the direction derivative, that is equal to negative gradient t, right? And you substitute it, you get negative 5 over 8 square root 41. Okay. So example 7 you can do. So this is a homework. They're the same. They ask you for the rate of change, direction at P, which rate of change is a maximum, and find is a maximum value. Okay, rate of change mean only vector is given, so find the unit vector. Magnitude maximum. Okay, maximum means magnitude maximum, and the maximum itself will be directional maximum. Okay, next subtopic will be, next is normal vector to a surface. The normal vector to a surface. A normal n to a flat surface is a vector which is perpendicular to the surface. A normal n to a non-flat surface at point P on the surface is a vector perpendicular to the tangent plane to that surface at P. So let's say I have, this is non-flat, then another one is flat surface. So say point n, normal vector. So as I put this, z is equals to fxy, flat surface, and this is also the bottom one is non-flat surface. So again, a normal n to a flat surface, okay, is a vector which perpendicular to the surface. Easy. Okay. A normal n to a non-flat, okay, to a non-flat surface at point P. Let's say I put this P. Okay. On the surface is the vector perpendicular to the tangent plane to the surface, to that surface. So we have tangent plane. Let's say this point. So the normal space will be perpendicular to the tangent. Therefore, for a non-flat surface, the normal vector is different depending at point P where the normal vector is located. Okay, it's going to be like this, because it is non-flat. Okay, it's a curve. So theorem: if f x y z equals to k is differentiable function and n denotes as a unit normal vector, okay, unit normal vector to the surface, then your n will be plus minus gradient f over magnitude of the gradient f. Okay. So this plus minus refer to different direction. Plus minus for different direction. Okay. So as usual, del f. Okay. Okay, let me explain. the theorem. So let a surface Z is equals to fxy. Okay. Then it is used to represent a surface by defining as f x y z equals to f x y minus z. Okay, which is equal to 0, or can be written as z minus f x y equals to 0. Thus f x y z equals to k, where the k is f x y minus z, or your k will be z minus f x y. Okay. Oh, see example 8. Find the unit normal vector. Find the unit normal vector of the surface at the indicate point A x e y plus y squared y cube equals to z cube at 1 0 negative 1. Okay. So solution. So f x y z will be x e to the power y plus y cube minus z squared equals to 0. Easy. Just bring to the left, or your minus z squared for both sides, left hand side and right hand side. So your n will be, vector unit vector normal will be plus minus gradient big F over magnitude of big F. Okay, and plus minus is a 4 different direction. So your del F will be fx, fy, fz. Okay, or you can do del f del x I plus del f del y j plus del f del z k. So this for fx will be ey, right? Ey, see this? Ey plus, and then nothing 0, sorry, nothing comma, and then fy will be xey plus 3y squared 0, and then we have differential respect to z. First one, second one, 0 will be negative 2z. Okay. Or we can write as ijk form, no problem. So at 1 0 negative 1, 0 negative 1, this will be e to the power 0, right, plus x e to the power 0, 1 times e to the power 0, and so on. You will get 1 1 2. Okay. So the magnitude of this f at 1 0 1 will be, this is big F, and it should have vector. We have square root 6, 1 square plus 1 square plus 2 square. So your n at 1 0 negative 1 will be 1 1 2 over square root 6. So n can be positive and n can be negative at any surface. So you can write as plus minus 1 over square root 6 1 over square root 6, 2 over square root 6. Okay. So tutorial 8. example 8 is taken from your tutorial, question 14 number 2. Okay, find unit normal vector to the cylinder x squared plus y squared equals to 25 at p equals to 3, 2, negative 3, 2, 4. So try to do this as your homework. You'll get plus minus three over square root 13, 2 over square root 13. Okay. Okay. For C, also you can do it by yourself. It is just a hemisphere. And then we go to divergence and curl. Divergence and curl. Okay. Okay. So at every region of space, there are two very important questions that we need to answer. First, question for divergence. Whether the particles are just passing through the region of space, or if the region of space generating the particles, or if the region space is absorbing the particles. Second question, for curl, whether the particles are swirling or not around the region of space. By finding the divergence and curl, we can answer all these questions. So why we need to find divergence and curl? Again, at every region of space, there are two very important questions. You need to answer first for divergence, second for curl. For divergence, whether the particles are just passing through the region, or if the region of space generating the particles, or if the region of space is absorbing particles. For curl, whether the particles are swirling or not around the space. So the divergence is an operator that measures the magnitude of a vector field, source or sink at given point. The divergence of a vector field is a scalar field that tells us each point the extent to which the field diverges from a point. The divergence of vector is a scalar. Vector field is a scalar. The divergence of a vector field F let's say F vector defined as F1 XYZ I F2 function of J plus F3 K. Okay, is defined as diff F, or in maths we will write as nabla dot F. So nabla is del is F is del over del X, del over del Y, del over del Z, dot with F1, F2, F3. So you will end up with del F1 over, so dot product you will get a scalar, plus del F2 over del XY plus del F3 over del Z. Okay. Okay. So if the divergence more than 0, so the region space generate the particle. Okay. if the divergence is less than 0, this is small to 0, divergence less than 0, the region space absorb the particle. Okay. If the divergence equals to 0, the particles just pass through the region. Okay. Space, region of space. Okay. So this is generate, this is absorb and passed through. Okay. So curl. Curl is a vector operator that shows the vector field's rate of rotation, that is the direction of the axis of the rotation and the magnitude of the rotation. The curl of a vector is defined as curl F. So we write nabla cross F. So this is ijk del over del x, del over del y, del over del z, and this is F1, F2, F3. Okay. Then so the tendency of the fluid to swirl, to swirl or spin. Okay, if the curl more than 0, del cross F more than 0, it is pointing upward, which means the rotation is counterclockwise. Okay, anti-clockwise rotation. If the curl less than 0, it is pointing the other way around, that is, pointing upward also, but the rotation is clockwise. Then if curl equals to 0, no rotational motion. Okay. Okay. Example 9. Find both divergent F and curl F. Curl F at the point 203 if x, y, z equals to z e to the power of 2x y I plus 2x z cos y j plus x plus 2y k. Okay. Okay. So solution. So divergent F is easy. Will be del dot F, nabla dot F. So okay, to remember this D dot, okay, curl cross, later I will show you. So it will become a scalar because vector dot with a vector. Okay, because it's a vector product also. So del dot F will be del over del x, okay, del over del y, del over plot with this function. This is z e 2xy 2xz cos y. Just copy from the question. X plus 2y. Then this will result as 2y z e to the power of 2xy minus 2xz sine y at 2, 0, 3. You just substitute x equals to 2, y is 0, z equals to 3, you will get 0. Your divergence equals to 0, which means the particles just pass through the Riemann space. Okay. Second, curl will be del cross C cross. Okay, remember. And then so del cross F I j k del over del x del over del y del over del z 2e 2xy 2xz cos y x plus 2y. So remember, you will get I minus something j plus something k. Okay, you have to close the first row and first column, first row and second column, and first row third column. Okay. So do it by yourself. You will get two minus 2x cos y okay, then you have minus 1 minus e to the power of 2x y, and then 2z cos y minus 2x z e to the power of 2xy. Okay, so add 2, 0, 3, substitute x equals to 2, y 0, z equals to 3, you will get negative 2, 0, negative 6. Okay, check. Okay. Okay. Okay, so next we move to properties of del, multiple operations. We can combine the grad, gradient, divergent, and curl in a multiple operations if f and g are differentiable, vector f and y is differentiable in f and g, small f and small g are differentiable scalar functions, then are differentiable vector functions. F and g are differentiable as scalar function. F and g are differentiable scalar function. Then first one, you have to remember all of this. F plus minus g del to del f plus minus del g. Okay. Then number 2, del f g equals to f del g plus g del f. Sometimes you need to know how to prove this. F over g equals to G del F minus F del G over G squared del dot peak F G equals to del dot F plus minus del dot G. Okay. Number 5, del cross F plus minus G equals to del cross F plus minus del cross G. Okay, we need more. And then number 6, this is famous, divergent grad F is equals to del dot del F. So this del dot grade F equals to del squared F, which is fxx, comma fyy zz. Okay. This del squared, that equals to del over del squared plus del squared over del y squared plus del squared over del z squared is a Laplacian operator. Okay. So if this is equal to 0, which means it is called a Laplace equation. Okay, we have more. 7. Curl grad F equals to del F. So if del cross del F equals to 0, or curl grad F to 0. So we can write in either way, either in a word form or in a mathematical notation form. This is cross. Okay. And number 8, grad diff F, divergent F, same as nabla or del dot, divergent is dot. Okay, D dot. Then 9, divergent curl F, same as cos F. So we can write as cos F equals to 0, or divergent curl F equals 0. Okay, curl. Number 10, curl F, so del cos F equal to del dot F minus the square F. Okay, so number 6 to 7, 6 to 10 is so important. Okay, may come out for your exam or may not. Okay, you see example 10. Okay, see example 10. If f equals to 2yz negative x squared y x over z squared, and then your g x squared yz and negative xy, and then they give you phi to 2x squared yz squared. So find, first one is del f phi. Okay, del dot f phi. So first find del dot f. So del dot f you can find, I already teach you, there's a gradient fx I fyj plus fzk. So you will get negative x squared plus 2xz. Okay, try to do. And then del dot f times with phi will be negative 2 negative x squared plus 2xz times with 2x squared yz cube. It's just given, it is given, so it is nothing, just expansion of algebraic equations plus 4x cubed yz to the power 4. Okay, done. So try to do it. Number 2, del dot g times with f, you will get 4xyz plus 2yz squared minus 2x cubed y plus x squared yz, and then the last one is 2x squared z squared plus xz cube. Okay, check. And then number 3, del cross f phi. So first you have to do the cross product, and then you have to times with phi. Still you end up with the scalar, vector. Then your answer will be 2 squared yz cube 2y minus z squared. Sorry, I think the first one is 0. Okay. Zero. Zero. 2x squared yz cubed times with 2y minus z squared, and then the last component will be 2x squared yz cubed 2xy times with 2xy plus 2z. Okay. Okay, k component. So next will be the final 2015 and 16 Sem 1. So this will be your homework. You can check the answer with me. Also, yeah, I think that's all for chapter 4, vector value function. So next we move to chapter 5. Chapter 5, that is line and surface integrals. So this is your last chapter for this course. Okay, goodbye.